Okay, so in the last set, we got up to the point where we were talking about why we call this analysis of variance, because we've partitioned the sum of squares into the model-based variation and the error or residual variation. So, you know, we want to be able to make a decision about the special case or restricted model and the larger or more general model and make sure it's a good fit to our data. So we're going to take two basic approaches for making this decision. We're going to use significance testing, F-tests mostly, and then we're also going to use information criteria, the Akaikis and the Bayesian information criterion. So we're going to go over, and this I would think you've seen before, just the basic ANOVA table. And in the ANOVA table, there's a row that has a label for that partition of the sum of squares. So we have for each row a different source of heterogeneity or variation. We also have parameters that are degree of freedom parameters that are also really important. So let's take a look at this table and we'll talk through it. And again, this should be review. So we have the source of variation that's model based. So this is what does the model account for in the heterogeneity of the responses. Here is the sum of squares for that model. This is like what we called SSM in the previous slide. Here's the degree of freedom associated with that. So generally this will be, in the CRD case, just the number of treatment levels, if we call that T minus 1, okay? And here is the mean square. MS stands for mean square, and that's really notice what this is. This is a ratio of a sum of squares over a degree of freedom. So what is that? That's a variance calculation, right? So this is just a estimate of model-based heterogeneity or variation. Then we have that improvement from model 1 up to model 2. Okay, so model 2 is the large model. Model 1 is the restricted. So there's going to be a difference. Remember, with the large model, we'll have a greater value, or it perhaps equivalent, but most likely greater value for this sum of squares than this. So this will be a positive number here, or perhaps 0 in the case that they're exactly identical. Then there's going to be a degree of freedom associated with that minus that, and then we get our variance measure. Then we have the error, and that's just the error associated with just random variation that's unaccounted for by the statistical model, and that would, the degree of freedom for error is big N, the total number of observations, minus R2, that large model, and then our MSE or variance calculation there. So there are some simple formulas that we'll just take a look at. I don't like hand computations of this because I don't know, it's just very tedious, I think, but let's make sure we understand it. First, Yij is the jth response in treatment I. So we have G treatment groups, so notice I varies from 1 up to G. So we have values that belong to group or level 1, level 2, on up to level G. But within each level, let's say we're in level 1, there are observations going from 1, 2, on up to N1. So we have N1 observations in level 1, N2 observations in level 2, on up to NG observations in level G. So then we can compute group means. So these are the things that we allow to vary, perhaps in the larger model. So for I equal 1 up to G, we can say that the ith mean is just the sum of all those observations in that particular group divided by the sample size for that particular group. That's all that is. It's really simple. So that's the mean response for the ith treatment. And then let y bar dot dot, so notice when we have a dot, that means it's summed over. The j in this case is summed over, but if we sum over the I and the j, we're getting the overall or grand mean. And notice that's just all the observations summed up. So every yij, so we sum across each group and across within each sample size within each group and divide by big N. And that gives us our grand mean. So let's say that we have a restricted model that is that all treatments are the same. And the larger model is that each treatment has its own mean. Then we can come up with the following values. So if the restricted model says that all treatments have the same mean, then R1 is 1, because we just have to estimate the mean, the grand mean. If the larger model is that each treatment has its own mean, then this would be G. Then we have SS1, which is the sum of squares associated with the restricted model, and that's just going to be that grand mean squared times n, which when we divide by n, that just gives us that grand mean squared, which is a form of a sample estimate for variance. Then we get SS2, which is going to sum over each treatment mean squared times it's weighted by its sample size in that group. So that the difference between SS2 and SS1, a little bit of algebra would show that if you take this and subtract this, you can get it into this form. Just a little algebra. And then finally SSE is going to be the difference between each Yij and the group mean. So take a look at what's inside these sums of squares here, because we're measuring the heterogeneity of each observation within its group here. So that's really truly random error or residual error. Versus here, we're looking at each deviation of the treatment mean from the grand mean. So that's looking at how far away is each treatment mean from the overall grand. So if these distances are short relative to this, we will decide that the restricted model is fine. If these are large with respect to this, then we'll decide we need the more specific larger model. Okay, so here's how we set up the ANOVA table. So notice we have the overall with 1 degree of freedom, the between treatments, and this will have a degree of freedom of G minus 1 here, and the error in minus G. And the mean square can be denoted as MSE or TRT for treatment, if you like. I like to use that notation, so I don't know in class that I'll ever write it out this way, but it's good to see it both ways. The line for the overall mean is, as Gary says, so boring that we usually leave it off. So you'll see in most software, this line will not be included because it is so boring. Okay, so note that any single observation can be thought of as a linear combination of all of these different means that we've been talking about, the grand mean plus the deviation of each treatment mean from the grand mean plus the deviation of each observation from its treatment mean. And algebraically, that's really simple and works out. Hence, we can square both sides of this equation, of this equality, and add it over all I and j, and we get the following. So notice what these are. This is the overall sum of squares, the group, the overall grand mean sum of squares, the treatment mean sum of squares, and the error sum of squares. So this is the equality that we make use of in this ANOVA table. So noticing that all of these give us that left-hand side. So the ANOVA just makes use of algebra, okay? So we say, let's assume we have normal distribution of each Yij, then the expectation of our mean squared error is going to be sigma squared. We're going to make that assumption. Under the restricted model, so remember the restricted model says that every mean can just be modeled using the grand mean, then our mean square for treatment would be exactly also sigma squared. Okay, so if we made a ratio of our MS treatment and MSE in that case, we get exactly 1 because it'd be sigma squared over sigma squared. And we get 1. But when this ratio of mean squared treatment over mean squared error is bigger than 1, then we have evidence that the group means are varying, that they differ in some way. So if the restricted model is not good enough and the expectation is of this mean squared treatment is actually bigger than sigma squared, then this F test statistic will be bigger than 1. And so we're just going to compare it. This is an easy case for our null distribution just being the F distribution with the appropriate degrees of freedom, so that we can find cases where F is substantially larger than it should be. When the null is true and our normal distribution is correct, then that F will be follow an F distribution with G minus 1 and N minus G degrees of freedom. And the null hypothesis will be rejected when the p-value of the F test is small, or the value of that F test statistic is large. Let's take a look at some examples of this in class using R. I don't want to do the hand computations because this is also review. I assume you did that in past courses. Okay, so when we get to class 2, we will take a look at using that F test, and that should be routine to us by the end of the hour. But we'll also take a look at these information criteria. This will be used in conjunction with the F test to assess fit of the models. Basically, these information criteria, and on the next slide, it gives us a sense of what they're all about. It takes, if L is the maximized likelihood for the data, you can think of this as the probability of the data under the model with the parameters in particular chosen. This likelihood is going to be as high as possible, and will make or be maximized when we have a good fitting model. Okay, so notice with both of these, we take -2 times the natural log of that maximized likelihood. And again, we want L to be big in this case, which means, like we said on the previous slide, models with smaller values of AIC or BIC are better. That makes sense in light of the fact that big L is good, or indicates good model fit. Then there's these penalties applied. So K is the number of parameters. So notice we get penalized for having too many parameters, okay? And then we don't get the lowest possible AIC. And here also penalized for for K being too big. So again, small is good for AIC, BIC because we want L as big as possible. So choose the model with the smaller AIC or BIC. AIC tends to choose models with more parameters than we would get if we just use the significance test, but the reverse is true for BIC. Okay, so I think taking both into account is a really good rule of thumb, and we'll take a look at these again in class for some applied examples. Okay. I'm going to skip this because this will be kind of included in our class demos. I just want to get to this point before my note time runs out. I want us to be familiar before class with this idea of the central value and the treatment effect. Okay, so notice any group mean, mu I, this is the true value for the group mean, can be broken down into this overall grand mean or central value and the treatment effect. So when we have it laid out in this way, it's easy to see that the treatment effects really tell us how a treatment mean varies from the grand mean. So it's that difference between the treatment mean and the grand mean. And when we estimate these quantities, that's how it still looks like. Okay? So when we're under the overall different constraints for the models, we can make overall conclusions, such as we can define constraints to put on our model. I think the first is the default in R, but I think intuitively the second just seems very reasonable. It says the grand mean is the mean of all the treatment means, which we know to be true, and we're going to enforce the constraint that the treatment effects sum to 0. We can force R to do it this way. We'll talk about this a little more in class.